Okay, we'll continue the numerical problems on the damped vibration. Okay, let's take the next problem. The measurement on a mechanical vibrating system. It is a system which has mass 10 kg. Mass is given and the spring can be combined to give equal spring stiffness. Stiffness value is 5 Newton per millimeter. You convert it to Newton per meter. So it is 5000 Newton per meter. Mass is given, stiffness is given. If the vibrating system have a dashpot attached which exert a force of 40 Newton when the mass have an initial velocity. I already told you, if damping force and velocity is given, then you will get a damping coefficient by using F is equal to Cx dot. Okay. What is asked in this problem? To find the critical damping coefficient, damping factor, logarithmic decrement and the ratio of successive amplitudes. Okay, given data are mass, stiffness, damping force and x dot, velocity. By the damping force and velocity you will get the damping coefficient, that is 40 Newton second per meter. Now you calculate what is Cc. You already know that Cc is 2m omega n. M is given and omega n is equal to square root of k by m. K value we have 5000 and m is 1000. Okay, k 5 by using this expression 2m omega n you will get a Cc value, critical damping coefficient. Next you need to find zeta. Zeta is C by Cc. C value is 40 divided by Cc. Cc value is 447.21. Okay, zeta. Next delta. If you know the delta value, then using this expression you can find this logarithmic decrement. Next, ratio of successive amplitudes. If you know the logarithmic decrement, delta is equal to ln by xn by xn plus 1. This xn by xn plus 1 is the ratio of amplitudes. This delta value it is calculated in the previous one. So xn by xn plus 1 it is equal to e raised to delta. You find what is this ratio. Okay. Next we will take one more problem. Vibrating system consists of mass 50 kg. Mass is given again. Stiffness is given 30,000 Newton per meter and damper. Damping is 20% of the critical value. See here, damping means C. C is 20%, 20% is 0.2, 0.2 of the critical value. C equal to 0.2 of Cc. C value it is 20% of Cc, that is C is equal to 0.2 of Cc. C by Cc is 0.2. C by Cc is nothing but damping ratio, that is 0.2. What is asked to find out? Damping factor. Damping factor means zeta, that is C by Cc. Next, critical damping coefficient. Critical damping coefficient 2m omega n. We have mass given value here and omega n is square root of k by m. Cc value you can calculate by this expression. Next, logarithmic decrement. Logarithmic decrement, delta is equal to 2 pi zeta divided by square root of 1 minus zeta square. To find the logarithmic decrement you need this zeta. What is zeta? C by Cc. C value C by Cc, you have already this zeta. Substitute this one and find the logarithmic decrement. Next, ratio of two successive amplitude. If you know already, delta is equal to ln xn by xn plus 1. Using this expression you can find what is the ratio of two successive amplitude. Okay, we'll take one more problem. Here the mass of a single damped vibrating system is 7.5 kg. Mass is given, it is 7.5 kg. It makes 24 oscillations. It is a system, when it is excited it is making 24 oscillations in 14 seconds. So number of oscillation divided by time, it gives the frequency, that is omega n. This omega n, that is in hertz, multiplying by 2 pi you will get in radian per second when disturbed from its equilibrium position. The amplitude of vibration reduces 0.25 of its initial value. Okay, see here the amplitude, the initial amplitude, that is x naught. Initial value is x naught. Okay, it reduces its amplitude, its initial value after 5 oscillations. So after 5 oscillations, what is the amplitude? That is 0.25 times of the initial value. So Okay, what you need to find out now, stiffness of this spring. Okay, by using this data, 24 oscillations divided by 14 seconds, you will get a frequency. This frequency is in hertz, multiplying by 2 pi, you will get in radian per second. Omega n is equal to square root of k by m. Mass is given, it is 7.5. Mass is 7.5. Omega n is, this is 10.77. So you will get the stiffness of the spring. Next, logarithm decrement. How to find the logarithm decrement? Logarithm decrement, we know that delta is equal to 1 by n ln of x naught by xn. What is x naught? It is initial value, original amplitude, initial amplitude, and xn is after 5 oscillations. He has given this sentence, after 5 oscillations the amplitude reduces to 0.25 times of the initial value. So this is initial value, and after 5 oscillations its value is 0.25 of x naught. So this x naught get cancelled. This is n, 5 number of oscillations. So you will get this delta, that is 0.277. Then damping factor. Damping factor is equal to C by Cc. Delta is equal to C by Cc. Now we have zeta equal to C by Cc, but we have no C data here. Okay, C value cannot be calculated here, so we need to find the damping factor some other method. Okay, we know that by this data you will see delta is equal to 2 pi zeta divided by square root of 1 minus zeta. So delta is also equal to 2 pi zeta divided by square root of 1 minus zeta. We know the delta value. If you know the delta value, then zeta can be calculated. That's it. Delta is equal to 2 pi zeta. This zeta can be calculated if you know the damping ratio. If you know the logarithm decrement. Logarithm decrement value is 0.277. It is calculated here. Okay, thank you.